Good morning, pre-calculus students, honors pre-calculus students. We're going to take a look at box problem number 5. So I'm going to sketch a box here. It may not be drawn to scale. And in this particular box problem, it says the base is 3 times the width. So I'll call this this side here x, and the other side 3x. And then I'll call the height y. We know the volume of the box is length times width times height. So x times 3x times y. So 3x squared y. We know the volume is 50, so I'm going to substitute that in. The second, so that's equation number 1. As I mentioned, we're always going to have 2 equations. One is called the constraint. The other one is going to be the min or max function. We need a surface area. So let's just review surface area. We got the front of the box. I'm going to highlight that in yellow. So the front of the box, the area is xy. And we have the back of the box. Then we have the side of the box, which I'm going to highlight in green. That area is 3xy. We have a left and a right, so there's another 3xy. And then in blue here, we got the top, and the top of that box is going to be, what's it going to be, 3x times x, so it's 3x squared. And there's a top and the bottom. The reason I did this in red is this is the top and the bottom. It is a different cost than the sides. So in blue I got the sides, and then the red is the top and the bottom. So if you do a little math here, when you add these up, you got 6, 7, 8xy plus 6x squared. And it tells us that the cost for the sides are $6 and the top and the bottom. So I'm going to write a new function. The cost is going to be 6 times 8xy plus 10 times 6x squared, which is 48xy plus 60x squared. Now this cost function has 2 variables, so we're going to go back to the red equation and solve for y. You could solve for x. It's easier to solve for the easiest variable. So 50 over 3x squared. Then we're going to go back to the cost equation and substitute that y. So the cost is going to be 48x times 50 over 3x squared plus 60x squared. If you simplify this, you will get 800 over x plus 60x squared. So this is the function we want to minimize. So we're going to pull out our graphing calculators. We're going to type that into our calculator. I like to start at zoom 6, so zoom 6. And I see part of the graph. So if you look at this function here, if you just were to plug in 1, you should see that you're about at 860. So I definitely know I need to go higher. I might also have to go a little bit to the right. So as we discussed in class, I'm just going to change this maybe to say 50. And I'm going to make the height, at least if it's 1, I know I'm up at 1,000 or 860. So I'm going to change it to 1,000 because it's a little higher. Again, I may have to adjust these. I'm going to hit graph. And I do see the function. I see that minimum. So I went a little bit too far, so I'm going to go back and adjust my x max, maybe just to 15. I don't need to go so far out. All right, and then on the TI, I'm going to go second trace. On the Casio, you have the G-solve. I want the minimum, so I'm going to go a little bit to the left and hit enter, and a little bit to the right and hit enter. And then for guess, I'm going to hit enter. So the minimum occurs at 1.882 and 637.60 if I were to round. So going back to the problem, in the left corner here, the minimum cost is the 637.60. And in the right corner, I'm going to do the dimensions. So we know x is about 1.882 feet. I also need to calculate 3x, and then I need to calculate y to get the dimensions. Now, if this was the last thing you did, the calculator will remember the value of x. Just to convince you of that, I'll hit x there. So we need a 3x. So the other dimension is 5.646 feet. We also needed 50 divided by, make sure you put parentheses here. I believe it was 3x squared. I'm going to check that. So 4.7052 if I were to round. So the other dimensions of this box are 5.646 feet and then 4.7052 feet. So hopefully that helps you with the box problem.